Okay, let's consider a situation with an object on an inclined surface and analyze the motion using Newton's second law. So we have the steel force roller coaster at Dorney Park pulled up the first hill at a constant speed by a chain. We know the hill is angled 28 degrees above the horizontal. We've got the speed that the train moves at, a resistive force, and the mass of the train. We want to calculate the magnitude of the force applied to pull the train up the hill. Well, first thing to do is to recognize all the forces that are acting, which means we're going to need to draw a free body diagram. So then I've got my picture of the roller coaster. And so it's being pulled up a hill. So here's the roller coaster train. Coordinate system, 28-degree angle. Now we're ready to label all the forces that are acting on the roller coaster. Field force, we've got the weight, vertically downward. Weight, which again we know is equal to mass times gravity. And then contact forces. Well, there's a chain that's pulling it up the incline. So then I'm going to call that the force applied. The train is being supported by the tracks. That support force, or that normal force, is going to be perpendicular. So I'm drawing at a right angle to the track. And then we know that there is a resistive force of 320 newtons opposing the motion. And that's our free body diagram. In part A, we want to calculate the magnitude of the force applied. So that's this force here. Okay, we're going to use Newton's second law. Before we can do that, though, we're going to have to resolve the weight into components. Remember, when we have an object on an incline, we're going to shift our xy axis so that x is along the incline and y is perpendicular to the incline. So then the applied, the normal, and the 320 all line up in either the x or the y direction. However, the weight does not. And so we're going to resolve the weight down into two components. One that is at a right angle to the incline and one that's parallel to the incline. So the one at the right angle would be in the y direction. I'm going to call this FGY. And then one along the incline, the component of the weight, FGX. By the geometry we did in class, this 28 degrees will come over here. And then you've got a right triangle right there where FGY and FGX are the two components of the weight. So we're going to find those values. Let's calculate the weight first. That's mass times gravity, so that's the 3250 kilograms times 9.8. And so we get a value for the weight of 31,850 newtons. That's the hypotenuse of our right triangle. So then I can go cosine of 28 degrees. The side adjacent to the 28 degrees is FGY. And then the hypotenuse is 31,850 newtons. And then sine of 28 degrees. The side opposite is FGX. So that's FGX over 31,850 newtons. So then doing the calculations, we get our y component to be 28,121.88 newtons. And our x component to be 14,952.67 newtons. Now, effectively, we have replaced the weight, and we're only dealing with the components of the weight. So again, back to part A, we want to calculate the applied force, The applied force is a force in the x direction. So then Newton's second law, net force is equal to mass times acceleration, all in the x direction. Well, given that this is moving at a constant velocity, we know the acceleration is going to be 0. So all we have to do is create an equation of our three forces that are in the x direction and then solve for the applied force. So the applied force will be positive. It's in one direction. FGX and the 320 are in the other direction. I'll put those in as negatives. So positive force applied combined with a negative 320 newtons combined with a negative 14,952.67 newtons is equal to 0. When we do our algebra and solve down, we get our applied force is 15,272.67 newtons. And again, the direction of that force is shown on our free body diagram. Part B. The lower picture shows the train traveling down the hill. So it's gone up the first hill, over the top, and now it's going down. Okay, the hill is inclined 66 degrees, and the resistive force is 720 newtons. And we want to calculate the train's acceleration down that first hill. Well, we're not on the up part, we're on the down part, which means we've got a new free body diagram. So I'm going to give us a little bit more space here. And hopefully that's enough. Okay, so I'm going to draw a new free body diagram where we're going down the hill. So we've crested the top and now we're on the downhill. So here is the train. So we still have the weight. And the weight hasn't changed. So our weight is still the value of the 3180 that we calculated right there. We still have a normal force. We have a frictional or a resistive force, but it's a different value now because we're traveling down the hill and the motion is different. So that value is 740 newtons. And we want to calculate the acceleration. What's going to accelerate along the incline, that would be in the x direction. So then we're going to want to sum all the forces in the x direction. Well, our angle has changed. It's 66 degrees now. So then we're going to need the x component of the weight. So I'm going to have to do a little trig to find that x component. So then FGY and FGX in our right triangle there, giving us a little more room here. I'm going to just slide that off of there. And now we can do the trig to find the x component. Remember, our 66 degrees would be right there. And so that's the adjacent side. And this is the opposite side. I need the opposite. Sine of 66 degrees. FGX over the hypotenuse, 31,850 newtons. So then when we solve down for that FGX value, I now get 29,096.42 newtons. So now when we sum all the forces in the x direction, I have FGX and I have 740. The chain's no longer attached. There's no applied force that's acting on it at all because nothing else is in contact. The chain's no longer in contact. It's going down the hill because gravity is pulling it down the hill. So when we sum the forces, we don't have the three forces we had over there. We only have two. FGX in one direction, 740 in the other direction. So then I'm going to call down the incline a positive. So then it'll be positive 29,000 96.42 newtons, combined with the negative 740 newtons, and that's equal to mass times acceleration. Well, the mass of the train was the 3250 kilograms, and then times the acceleration. So combine your forces here, and then divide by the 3250 kilograms. So that gives us an acceleration of 8.73 meters per second squared. Now, acceleration is not directly drawn on the diagram, so I am going to want to indicate a direction. And so the direction would be down the incline. So, and when you're problem solving, you have to look at your given situation. If you have an acceleration, you have an MA because you have extra newtons. If you have a situation of equilibrium, you have no extra newtons, so then you have a 0 on that side. In either way, you solve down. Ponder physics.